All right. So, let's see. Last week we got through most of Chapter 10 material in class, actually. I think the last main things that I want to look at in the section of Chapter 10 specifically is look at a example of thermal expansion that I have prepared that involves some trigonometry just to help brush up on that, and then talk about gas law, ideal gas law a little bit, which hopefully will be reviewed depending on how much chemistry you've had. But to start with, how are you guys doing? And do you have any questions about any content from the past little while as you've been reviewing things or working on homework? Okay. Pardon me. All right. Well, for now, let's just go full steam ahead. We might be able to get through Chapter 10 in the next hour or so. So let's go ahead and get started. Where were we? Oh, yeah. Whoops. Remember to show my screen this time. Whoops. All right. Put this on camera. Okay. We're talking about thermal expansion. And I kind of wish that I had a certain demonstration I could do for you, but I'll save it for when we meet up for lab this week. Lab this week will be we'll do two labs whenever we meet up in person. The first of the two will be a thermal expansion lab, and I'll demonstrate a particular device that I like doing for this time of the semester, this time of the class. And additionally, we'll do one on heat capacity, which are going to start with Chapter 11 this week. We left off talking about thermal expansion and looked at the formula for that, looked at some scenarios where it occurs, and the fact that it can be pretty disastrous if engineers don't take it into account. These railroad tracks being a particularly egregious example of what happens when the rails will inevitably grow in the heat of the summer but don't have room to. I'd like to put some math to an example like that. So this is not a very realistic scenario because I hope no one would build a bridge like this, but I designed this example to kind of just show the extremes of what could happen if built horribly wrong. So, good architects and engineers must take thermal expansion into account. Let's say that we have a bridge that is spanning a 250 meter long gap. That means that on the day it was built, and we're going to say that just for the sake of the extremes, it was built on the coldest day of the year, 45 degrees Fahrenheit. And at that temperature, the steel was 250 meters long. It fully spanned the gap. But if that was the dead of winter, it'll get much hotter during the middle of summer. So let's say that in summer it gets up to 100 degrees Fahrenheit. During that time, the gap itself, the actual space that the bridge was covering, wouldn't really change size. But the bridge itself will. So the bridge itself is now longer than 250 meters, so it doesn't fit within the same 250 meter gap anymore. And again, if a bridge was built like this improperly, what would likely happen is that the bridge would kind of buckle and bend upwards, kind of like, literally it would bend, assuming it didn't just break completely. But for the sake of extremes, for the sake of extremes, we're going to say that rather than bend upwards like this, as it grows, it's going to shunt upwards like this on an angle. So the new expanded roadbed is now the hypotenuse of a triangle. So we're going to be able to use our old trigonometry tricks to help us look at this one. So, 45 degrees Fahrenheit, bridge was this long. 100 degrees Fahrenheit, the bridge has grown. The expanded roadbed is now the hypotenuse of a right triangle. And it's up to us to figure out how elevated the far right side of this bridge is. Because if it shunts upward on one side like this, now it's above where it's supposed to be on the other side. And depending on how much it shunted upwards, maybe it's a few inches and a car can drive over it. If it's more than a few inches, that's going to be a problem. So we got to figure that out. Again, this is a big example of how not to build a bridge. So, what we know our starting temperature, our starting length, our ending temperature. We don't know how long it gets, but we'll be able to use some trig to help us with this one. For my math, I've gone ahead and drawn a right triangle here to represent the situation. The horizontal leg of that triangle is going to represent the original cold day length of the bridge, when the bridge bed itself was actually flat and spanning the 250-meter gap. It's going to expand and grow to some unknown length, and that's going to be the hypotenuse of this triangle. So the hypotenuse is our length final on the hot temperature. We don't know what it is yet, but we know it will be the hypotenuse of the triangle. And even though the bridge itself has expanded, the gap it was spanning is still the same size. And so that number remains unchanged. That 250 will stay as the horizontal leg of the triangle. The remaining leg, delta, I'm labeling it as delta H here. This is the change in height. So this was the roadbed, now this is the roadbed. It's physically been shunted upwards, and we need to figure out how far upwards will it be shunted as a result of this. So I always recommend listing your variables, labeling your variables, and drawing pictures whenever they could be handy for a physics question, especially if there's triangles involved. So, this is going to be the triangle that we use for our small amount of trigonometry. Additionally, one other thing we're going to have to do is, we were given temperatures in Fahrenheit, because that's usually what the weather in America reports in. But our formulas are going to need either Celsius or Kelvin. So I've gone ahead and converted the Fahrenheit temperatures into Celsius. Excuse me. 45 Fahrenheit will be about 7.2 Celsius, and 100 Fahrenheit will be 37.8 Celsius. My handwriting's pretty bad. I realize that 7 looks a little like a 1. My apologies. That is 37.8 degrees Celsius. All of our formulas need either Kelvin or Celsius. Kelvin's your best bet, but Celsius will work here because the formula we want, the thermal expansion length formula, specifically has delta T in it. Delta T means delta C or delta K is valid here. So, we have our original length. We don't know our final length or H, but we do know the change in temperatures. So we can begin looking at our change in length formula. Delta L equals original L, delta L over original L equals alpha times delta T. Start filling in some blanks here. Delta L is the same as L final minus L initial. We know that initial length, the original gap was 250 meters across, so we'll plug 250 in for L initial, both in the delta L and also in the denominator here. So we'll use that number twice. On the right side of the equal sign, we know our change in temperatures. Final is 37.8, and our initial is 7.2. Again, delta is always final minus initial, so we'll have the hotter one minus the colder one to show that the temperature increased. That'll show that the length increased. Last thing we need is alpha. We need to know the coefficient of thermal expansion for this particular bridge. This particular question says that our bridge is made out of steel. So that is our invitation to go to this table within the notes. Look at the entry for steel, average coefficient of linear expansion. For steel, it is 11 times 10 to the negative 6th. And so that will be what is plugged in for alpha. That leaves the last unknown in our formula as LF. So to solve for that, I would recommend solving for the right side. I'm going to multiply alpha by the change in temperature, then multiply 250 over to the right side, and then add 250 over to the right side to arrive at LF equals 250.084 meters. Now that is a growth of 0.084 meters. That's about 8.5 centimeters, which isn't a lot. Full disclosure. That is not, like, if you were just watching this, if you just had this piece of steel sitting on the ground, not installed as part of a bridge, and were just letting it expand while sitting still on the ground, you probably wouldn't even notice that, especially if it happened over time. That's still not a lot of growth. The weird thing that happens here is actually the trigonometry. We now know LF, so this term we found is the hypotenuse. So that 250.084 goes here on the triangle. Now we know two sides of the right triangle, and in order to find the third side, I recommend consulting the Pythagorean theorem. A squared plus b squared equals c squared. The only rules about which number goes where in this formula is that the hypotenuse always has to be the c squared term. So, what we just found is the hypotenuse. That'll be plugged in for c. One of our original legs can go in as either A or B. So I'm going to put the 250 in for A and the 250.084 in for C. And that will just let us solve for the remaining leg of the triangle, B, which I'm also labeling as delta H. So the change in height as the bridge is shunted upwards due to this expansion. To find this answer, I'm going to recommend squaring squaring the right side, then subtracting 250 squared over to the right side. Make sure to do the squareds before the subtraction. That's important. PEMDAS, order of operations, exponent always happens before subtraction. Then, once you've got b squared equals number, take the square root of both sides, and you should end up with b, which is going to be our delta H, equals 6.49 meters. That's 6.5 meters shunted vertically upwards on that side. And if you don't have a good mental sense of scale for meters, that's about 20 feet. The bridge got shunted 20 feet up in the air because of 8 centimeters of thermal growth. No bridge has ever been built like this, to my knowledge, which is good, because if it was, bad things would happen. Frankly, this would be a problem before it had even grown to this extent, because, you know, as if one end of the bridge did just start creeping upwards slowly, you'd hit a point where a car could not get safely on or off anymore, long before it was suddenly 20 feet in the air. So, I've been mentioning verbally that thermal expansion can be disastrous if not taken into account. My goal is for this to show a numerical source for how bad it could be when not factored in. Please let me know if between my handwriting or just the work itself, if you guys have any questions or issues with how this work is presented, how this particular question flowed, please let me know. There is one similar question on the homework. It looks very similar, and I'm actually inclined to go ahead and show you guys just to point it out. Whoops. Question 4 on the homework. It shows a similar setup, except instead of one solid length of steel, it's 2 separate lengths of steel that are expanding, which is a slightly better way to build a bridge. It is slightly better for taking care of this sort of problem. It will work very similarly, except instead of one big triangle, it's going to be 2 smaller triangles. That is, as far as thermal expansion goes, that's the end of the normal thermal expansion stuff within the notes, and at this point you should have all the information needed to cover up to thermal expansion questions in the homework. I'll move on to gas law next, which should finish up chapter 10, but first, just going to open the floor up real quick. Any questions or issues related to the question that I just looked over, or thermal expansion as a whole? We can revisit it any time. Just wondering if there's any questions right now. Take that as a no for the moment. Let me know if any issues come up. For now, let us continue onwards. So, all materials will expand thermally. That is, and they don't just get longer, they will expand in all 3 dimensions as well. This is why, if we look back a little bit, there is also the equation for volume expansion of materials. So as temperature increases, it will increase in size in all 3 dimensions of 3D space. Now, solids are easy to measure in this regard, because if it's, say, a big rectangle, you can just take some measuring tape and physically measure each axis separately from all the others, and you can monitor them as the object heats up or cools down. But solids are not the only thing that expands. All phases of matter will do this: solids, liquids, and gases. And yes, this is the one I want to be on. My mistake, sorry. And I want to mostly focus on the expansion of gases for this next part, because physicists and chemists, a lot of scientists in general, have been studying the expansion of gas over the years because gas is a very interesting state of matter. We consider solid objects to have both definite shape and definite volume. A certain block of steel will remain a cube and will remain at a certain volume at a certain temperature indefinitely, until you proceed to either permanently change its shape by breaking it, or you change its volume by heating it up, cooling it down. Liquids have definite volume but no definite shape. A gallon of water will always occupy 1 gallon of space at a specific temperature, but the water can change its shape to fit its container. But its volume stays constant at a specific temperature. Gases have neither definite shape nor definite volume. Like liquids, gases can also change shape to match their container, but in addition, gases, even at constant temperature, can have their volumes changed. For example, say you go to a party store and you get a large tank of helium. That tank has a lot of helium in it. And that helium is pressurized. It's all been jammed in there with an extreme amount of force to get as much helium within the canister as possible and keep it in there under pressure. There is a tremendous amount of helium atoms in there, and normally, at room temperature and standard atmospheric pressure, the volume of that helium would be a lot bigger than the volume of the tank itself. And you can see this when you start using the helium to inflate balloons. If you have a helium canister about this big, you could probably fill hundreds of balloons that are about the same size as the tank before the tank runs out of helium. So there's a tremendous amount of helium jammed in there because gases have no definite volume. If you exert more pressure on a gas, you can force its volume to change even at the same temperature. So gases do undergo thermal expansion. They absolutely do. If you heat a gas up, it will try to expand. But gases are unique in that there's properties other than temperature that affect their volume. And this principle that I'm dancing around is referred to as ideal gas law. And I'm hoping that this is sounding familiar. Most of my students here are either bio or chem majors, and that means they've had some amount of chem classes in the past. And in chemistry, ideal gas law comes up pretty frequently. So my hope is that this is review. My hope is that this is sounding familiar to you. The formula that's going to cover this concept should be one my hope is that it's one you've seen before. The formula in question is the ideal gas law formula, PV equals nRT. I've had some teachers refer to it as PVNRT, which is a pretty good, silly way of remembering it. The purpose of this formula is to show the relationship between all of the different aspects that can affect the volume of a gas. Looking at this particular formula, the V term in it represents the gas's volume, and the other variables here that can affect the volume of a gas, one is its current temperature. So yes, gases will thermally expand. If you heat it up, it will try to get bigger, it will be under more pressure, so that is absolutely one of the things that matters here. But the other factors involved are the pressure the gas is under. If gas just exists in the atmosphere around us, then it's under one standard Earth atmosphere's worth of pressure. But if you increase the pressure on a gas, if you are literally squeezing it, it's going to compress. It's like when you squeeze a balloon. As long as it doesn't pop, the balloon will get smaller in your hands as long as you're exerting more pressure on it. It's the same thing with the helium crammed into the gas tank. There's a lot of helium gas that's been put under extreme amounts of force and pressure to physically jam it into a smaller volume than it would normally occupy at a specific temperature. Meanwhile, if there's less pressure on something, the gas will be allowed to expand to larger than it would normally be. That's like when you allow the helium back out of the tank and it expands to a bigger volume once it's no longer under that extreme amount of pressure. Say you put it in a balloon, or you just open the tank and let it flow out into the atmosphere around you. This is additionally one reason why Earth's atmosphere gets so much thinner the higher you go in elevation. If you go up to the top of a mountain, air gets thinner, it gets harder to breathe, it gets harder to boil water too. Specifically because up there on mountaintops, there's less air pressure. The volume of the air around you is allowed to be bigger than it would be on Earth's surface at the same temperature. So, temperature affects the volume of a gas, pressure affects the volume of a gas. The last relevant term here is N. This should be familiar if you've had chemistry before. N represents the number of moles of gas that is present. That is specifically just a measurement of how much gas is there. N is number of moles. Moles is just a measurement of how many atoms or molecules of something are present at one particular time. For example, say you have a helium tank that has 1 mole of helium in it. That would be 6.0221409 times 10 to the 23rd atoms of helium jammed inside of that one canister. So this number here, hopefully this is a review, is Avogadro's number. It represents the number of particles per mole. If you have 1 mole of anything, you have this many particles of it. 2 moles of anything, you'd have twice this many particles of that substance. What this just means is the more of a substance, the more of a gas that is present, the naturally more space it's going to want to occupy, the naturally more pressure that gas is going to exert on its surroundings. Say, I'm going to use balloons again as an example. If you're inflating a balloon, the air inside of a balloon takes up more space the physically more air you put in it. So as you exhale and as you inflate the balloon, you're putting physically more moles of air, more air molecules into the balloon, therefore it ends up taking up more space. So N is just number of moles. The last variable here is R. This is a constant. It's the gas law constant. And depending on what table or what version of this formula you look up, you'll get some different numbers for R. R is just designed as a constant to try to scale all of these values such that they are adequately scaling with one another. It's just a constant designed to rectify all the units and make sure everything is the right size. And so R changes depending on what units you use. For example, there's multiple units of pressure and volume that you could use in this formula. Take volume, for example, because it's kind of the main thing we're looking at right now. The metric system has loads of different units for volume, including but not limited to liters, meters cubed, millimeters cubed, centimeters cubed. There's lots of different ways to describe volume. And similarly, there's loads of different variables, measurements for pressure as well. I'd say the 2 most common ones are pascals and atmospheres. So, just for context, right now on Earth's atmosphere, you are under 1 atmosphere of air pressure, and that 1 atmosphere of air pressure is equal to about 101,325 pascals. So again, just 2 different units to describe the same thing. And which value for R you use depends on what values for what metrics, you use for P and for V. Right now, the version of R I have here in these notes is in terms of liters for volume and atmospheres for pressure. If, say, you were working a question that had meters cubed and pascals, you'd want a different R value here. I'll try to make sure that all those R values are available to you in constant tables and in notes as they come up. For right now, this is the one that I find the most simplest because liters and atmospheres, pretty straightforward metrics. So if you are using liters and atmospheres for P and V, then you would use 0.0821 as your R value. So that's just a constant. It'll stay the same as long as you're using the same units. And so these are all of the things that will affect the volume of a gas, even more so than just temperature by itself. So, to quickly utilize this formula a couple of times to show the relationships between how these things affect the properties in question. We're going to start with this first little blurb up here. What pressure is exerted by 0.75 moles of a gas at 25 degrees Celsius in a container with a volume of 1.5 liters? So we're told number of moles, temperature, volume, and we are asked for pressure. Look at our formula, pressure, volume, and RT. We want pressure, we know volume, we know N, we have constant values for R, and we know T. So we have everything we need to solve for pressure. So pressure is going to be our unknown, multiply it by our volume, 1.5 liters, equals number of moles times R. We are going to be able to use liters and atmospheres for our pressure and volume units, so we can use the R value from the previous slide. Lastly is temperature. Now, I said before that depending on the question, depending on the formula, you can use either Celsius or Kelvin for a particular formula. This is one of those formulas where you have to use Kelvin because it is specifically asking for current temperature, not change in temperature, current temperature. And if it's just T, you have to use Kelvin. So in my work here, I've taken the 25 Celsius and I'm adding 273 to it to within the formula convert it into Kelvin. So 25 Celsius is about 298 Kelvin, and that's considered standard room temperature. That correlates to about 75 degrees Fahrenheit. So this part right here is to convert the 25 Celsius into Kelvin to be able to use in this formula. Celsius will only work for delta T, since the change in Celsius is the same as the change in Kelvin. If it's just T, you have to use Kelvin, since that's a better metric of how much energy the substance has at a given temperature. So that just leaves one variable left to solve for, our P. We have everything on the right, so you can multiply everything over there, and then we're going to divide by 1.5 to the other side. And that should give us a final pressure of 12.24 atmospheres. That's a little more than 12 times the pressure that you are currently under right now, just from the air around you. So this is a pretty well pressurized container, actually. And given that it's at standard, like a normal Earth surface temperature, that pressure is primarily because of the fact that you're trying to jam a lot of mole. 0.75 might not seem like a lot of moles, but it is still a lot of particles, since 1 mole is this many particles, Avogadro's number. That's a lot of material to jam into a small vessel. So that's a lot of atoms put into a relatively small container, and so the whole vessel is going to be under more pressure than it would be just from the atmosphere around it. So the numbers to show that amount of the material present does affect both the pressure and the volume of your gas. Then, if the temperature is increased by 5 degrees Celsius and the volume is reduced by 0.25 liters, what effect will that have on the vessel's pressure? Before I go over the notes, before I go over my work, I just want to briefly get you thinking about if you had some amount of gas. We'll just look at each of these changes one at a time. And you had some amount of gas and you increased its temperature. What effect would that have on the pressure and volume separately? You have gas in a vessel, you heat it up. Normally, if you heat anything up, it's going to want to expand. So, increasing temperature, we know, can increase volume. But because on, again, the subatomic level, if you think about what thermal energy is, heat something up, its particles start bouncing around more, bouncing off of each other more. And so increasing the temperature of this particular gas can increase its volume, but it also could increase the pressure inside of the container, because as the particles inside are bouncing off of each other more, the gas particles will bounce off of each other more, and that will cause the gas to try to expand. The particles will also be bouncing off of the wall of the container all the more. And so the pressure that the gas is under, it depends not only on how much pressure is coming in from the outside, say how much you are squeezing the container inwards from the outside. The pressure also depends on how much force the gas is exerting outwards on its own canister. So if you take a vessel of gas and heat it up, its particles are going to bounce off of each other more, bounce off of the walls more. They're going to exert more pressure on the lining of its own vessel. And that will also, increasing temperature can also drive up the pressure for that reason. So just increasing the temperature could make the pressure bigger, depending on whether or not the gas is allowed to expand or not. But that's not the only thing we're changing here. We're also going to reduce the volume of this particular vessel. We're heating up, but we're also forcing it to shrink at the same time due to increased forces from outside of the vessel. So, looking at the formula here, if you leave V, N, and R alone, if V, N, and R are constant, and T gets bigger if you increase temperature, then P will also go up. P and T, as long as everything else stays constant, are directly correlated. If V, N, and R remain constant and you double temperature, P will also double. So P and T are directly correlated. But let's say that you leave N, R, and T alone, and instead you change the volume. P and V are inversely correlated in this formula. If N, R, and T remain constant, so let's just say the entire right side of this formula equals 1, for simplicity's sake. The entire right side of this formula equals 1. You could get that answer of 1 if, say, P and V were both equal to 1. 1 times 1 equals 1. But you'd get the same answer if V was 2 and P was 1/2. 1/2 times 2 would also equal 1. So, if N, R, and T are constant and you decrease volume, pressure would increase to keep up with it. Again, if you take a balloon and squeeze in on it, the balloon will be under more pressure. You're literally exerting more force on it from the outside. And the gas inside of it will also exert more pressure against you. Newton's third law, you're pushing on it, it will push on you as well. So if you increase the pressure from the outside of the vessel, the gas inside, when forced to shrink, will also increase the pressure back on you. And this is why, if you squeeze on a balloon, it's likely eventually going to pop. You squeeze on the balloon, parts of the balloon are going to bulge out between your fingers, and if you keep increasing the pressure you exert, the gas inside will continuously be under more and more pressure, and eventually the physical rubber of the balloon can no longer handle that pressure, and it pops. So, P and T are directly correlated, whereas P and V are inversely correlated. Typically speaking, if you decrease volume, you will increase pressure. You can see that again with the helium tank. There's a lot of helium crammed inside of that tank. So you take an amount of helium that normally occupies this volume and physically cram it into a container that's this size, it's going to be under a lot of pressure. It'll take a lot of pressure to get it in there, and the vessel's going to stay at that pressure until all the helium is released, which is why if you open the valve to a helium tank, it's going to stream out very fast. It wants to escape. It doesn't want to be under that pressure, and it's going to keep exiting the vessel very quickly until it's all gone and the pressure levels equalize. So, for this second hypothetical question here, we have increased temperature and decreased volume. looking at the formula and how P, V, and T are all correlated, driving T up and V down, both of those changes by themselves could drive pressure up. And since we're doing them both at the same time, pressure should definitely go up from both of those changes, and the math will end up supporting this. So we're going to use the same formula, PV equals nRT. We want to solve for a different pressure this time, so we'll plug in our reduced volume. 1.5 liters is the original, and we're taking away 0.25 liters. So I've put in 1.5 minus 0.25. My handwriting is even more atrocious in retrospect. I apologize. Again, if my notes are hard to read at any point, please call me out on it. That's equal to, number of moles of gas will stay the same here. We're not changing it for this question, but as a general rule, like how P is directly correlated to T, P is also directly correlated to N. If you increased N, that'll make the entire right side bigger. That would also make the entire left side bigger. So if we did jam more moles of gas into this container, pressure and possibly volume would also still rise. But for this math, we're going to keep N the same. R will also be the same because we're still going to use atmospheres in liters for P and V. Last thing that changes, good morning. Had someone else join. Oh no, did I lose signal? Is that why I heard it bang? Have I been gone for a while and didn't notice? My mistake. I've just been... How long have I been gone and just talking at nobody? Okay. Sometimes when my signal cuts out, I'll drop out of the call, come back in, and I won't be presenting my screen anymore, and I don't necessarily know how long I was gone. I apologize for that. I'll continue from where I was, but if it sounds like you missed something, I'll go back. I'm sorry about that. So, in our new version with our reduced volume and our increased temperature, and an R the same, volume will go down. We started at 1.5, we're going to subtract 0.25. And our T, originally we were at 25 Celsius. We still need to convert that to Kelvin, but we're going to increase it again by 5. So what I have here written is 273 plus 25 plus 5, which is really the same thing as 237 plus 30, which should be about 303 Kelvin. So again, since it's just T, not delta T, you have to use Kelvin for this one, for gas law. Performing roughly the same algebra as before should give us an increased final pressure of 14.93 atmospheres. So as discussed, both separately increasing temperature and decreasing volume would both separately drive pressure up. We did both at the same time, so they really drove the pressure up. We went from about 12 to about 15. So a noticeable increase. If you were under this amount of atmospheric pressure, you would notice the change. It'd be pretty substantial. So both things happening at once had a more profound effect than just either one of them happening on their own. And so, gas law ultimately is just the formula that describes how all of these things are related as it relates to the volume of a gas. Now, tabbing back to the thermal expansion slide real quick. We have this formula here for the volume expansion of anything, really. All things, when heated, will expand in terms of their volume. This formula works the same way as the length one. You're just using units of volume and beta instead of units for length and alpha. This still applies to gases. Gases still undergo this process. They still use this formula. For example, if we look here at this chart of beta values, it lists several liquids here, but it also lists two gases, air and helium. They have beta values because you can use this formula to describe the thermal expansion of gases. The main thing to keep in mind, though, is that for liquids, this works just fine, because liquids have definite volume at a specific temperature, which is why most of the values listed here, alcohol, benzene, all the way through gasoline, are for liquids. As for gases, this does work, but this particular formula, if you are using it for a gas, assumes that N and P, pressure and number of moles, remain constant. This particular formula does not factor those in because for solids and liquids, N and P don't matter. Solids and liquids their volume is not affected by pressure and number of moles like gases are. So for solids and liquids, this works completely fine. Gases, gas law is your safer bet for, say, tracking how much it will expand or contract with temperature. This formula will also work, but it assumes P and N are constant. It doesn't factor those in because it doesn't need to for solids and liquids. It will work for gases as long as P and N are constant. If P and N are not constant, you'll need to use, gas law, ideal gas law instead. It's worth noting. And with that, that is the bulk of the material, that is all of the material that this course officially labels as Chapter 10. Just the processes related to temperature and how things change when their temperature changes. There is one more formula present in these notes, and I do want to address it again briefly. We've looked at it before, so this should look familiar. This particular formula here, I'm actually going to tab back to the original slide that it was on. Whoops. Machine's not working the way it's supposed to. There we go. This is the earlier version of the slide that had this formula on it. This formula represents, again, the relationship between an atom's energy level to its temperature. This formula is used, I believe, once on the homework. So I'm going to point out which question it relates to. Again, this is just the correlation between the kinetic energy level of an atom, the normal formula for kinetic energy, but then for atoms specifically, we have 3 times 2 times this constant times its current temperature in kelvins. Looking at the WebAssign homework, is, here we go. Question 10. Find the average kinetic energy in joules of a molecule of nitrogen at a certain temperature. This particular question here is designed for that formula. It's on slide 9 of the notes. It's also on the last slide of the notes. That is designed for that additional formula, Ke equals 1/2 times m times v squared, also equals 3 halves times K times T. So that formula will be used in the homework once. It refers to this specific question. So just wanted to go ahead and show that to you so you were aware of it as you were working. And that is the end of Chapter 10 content. How do you guys feel right now? Any current questions, needs, concerns, etc.? Okay? In that case, we've been going for about an hour. That's a standard class length of time. And as we are done with Chapter 10, I'm going to call a quick pause here. So you guys can pop out of the call, take a break, get a glass of water, and I recommend spending the next hour or so of class time looking over notes, pondering things, looking over the homework, and you can jump back in if you have any questions. I'll be here for the next hour. And tomorrow for class, one, if you have any questions that have come up as you're studying or working on things, let me know. And two, tomorrow we can also start looking at Chapter 11, which is, again, more heat and thermal energy. It's just a matter of what the textbook and what the homework arbitrarily labels as each category. But we've reached the official end of Chapter 10. We're going to be moving on to Chapter 11, which is really just more of the same. I'm just letting you know so that you're aware of which batch of homework certain formulas will apply to. For tomorrow, work on the homework and bring questions as they come up, and I will make sure that the Chapter 11 stuff is ready to go. For right now, we'll break here for right now. I'll be here for the next hour if you come back in with questions, and if you don't, I will see you later.